And that's, you know, I kind of anticipate you're at least going to get one of the two or maybe both again on your final, because they make you do everything, right, in the question. So a lot of people have trouble telling the two types of questions apart. In this solution, there's no E in your solution. So in your formula sheet, kind of on the last couple of pages on your printable equation sheet from OWL, I put in like how to tell these recursive questions from, you know, the last section, okay? So I put a note here. You guys used alpha, beta, and U and lambda. If you want to use that, go for it, okay? So here was our matrix earlier, and we had eigenvalues 2 and 3. And these were the eigenvectors, right? We solved this, I don't know, it's probably been an hour now. So assume matrix A is representing juveniles and adults. We want to find xt, assuming that x naught is 1, 1. So if here's my A matrix, here's my xt, c1 v1 lambda 1 to the t plus c2 v2 lambda 2 to the t. So c1 is a constant. So if you want to call it alpha and beta, go ahead. The first vector went with eigenvalue 2. So we put the vector and then the eigenvalue 2 is to the t plus c2, second constant, or beta if you want, second eigenvector 0, 1, eigenvalue 3 to the t. This is kind of like what we did yesterday, right? With finding the C1 and C2. If we're putting in this initial condition that x naught is 1, 1, then we're just going to put that right here. So the 1, 1 goes here. So now it becomes 1, 1 equals all of this. But because it's x naught, then really we're saying time is 0. So all these t's as these exponents can now be zeros. And of course, anything to the 0 is 1. So what we get is 1, 1 equals, and then here, what we can just do is make an equation from the top and make an equation from the bottom. So if you want to simplify a little bit here, you can, but you don't have to. Because really, we just know that, you know, this is going to be 1 equals C1 times negative 1 is negative C1 plus C2 times 0 is 0. So really, that's just what the top tells us. Similarly, for the bottom, it's just going to be everything times the bottom. So 1 is on the bottom equals C1 times 1, which is C1 plus C2 times 1. And then you can sub in. Okay. So if you want to write out this step in between, go ahead. But I usually just, you know, do top and bottom. So if C1 is negative 1, then if I put that back into here, then C2 is 1 plus 1 is 2. And then we can go back to this step here, right? So xt is C1, which was negative 1 times negative 1, 1, vector times 2 to the t, plus C2 is 2 times vector 0, 1 times 3 to the t. And that's our explicit solution there. Okay, questions? Okay, so if we want, let's say, x3, then we're just looking at what we just had, which was, let me write it again here. We had 2 times vector 0, 1 times 3 to the t minus 1 times eigenvector negative 1, 1 times eigenvalue 2 to the t. So if we want x3, we're just basically putting all the t's to be 3's, right? Okay. So 3 here, 3 times 3 times 3 is 27. So we get 2 times 0, 1 times 3 to the 3. And then minus 1. And then 2 to the 3. So 3 cubed is 27. So this we could say if you wanted, you can multiply this out and say, you know, 2 times 0, 1 is 0, 2. Or you can just do 27 times 2, 54. And then here, 2 times 2 times 2 is 8. So that's minus 8 times that. Now, how many steps you do is your choice, right? If you can do it in less steps or more steps, it doesn't matter. So if you want to write this out, 54 times this would be 0.54, and then we could say plus 8, negative 8. Either way, final answer should be the same. So kind of your choice, right? Okay, so it would be 8, and then 54 minus 8 would be 46. What does this xt tend to as t approaches infinity? Well, because 3 is a number larger than 1, 3 times 3 times 3 infinitely many times, that's going to go to infinity. And 2 is also larger than 1. 2 times 2 times 2 infinitely many times is also going to go to infinity. So it's going to be infinity plus infinity, so it's going to approach infinity. Okay? If it was, let's say they were both fractions like between 0 and 1, like a third and a half, then a third times a third times a third over and over and over again is going to go to 0, right? The same thing with a half. Okay. All right, so 7:45. So come back at 8 o'clock and we will continue on, okay? So have a good break. I'll see you back soon. obviously very annoying. So maybe I'll add that to that solution tomorrow, and then kind of update the solutions to show you how you can get from one to the other, just because I know it's kind of obnoxious. Well, the kind of, right? Very obnoxious. Okay. So this theorem is totally not required. It's on the top of page 271. But it just, they really just kind of touched on the word primitive matrix, but they didn't really talk about it, which is fine. But basically, if you have a matrix A that has all entries that are 0 or positive, and you keep doing a squared, a cubed, and all the zeros go away, it's primitive. And so, but what we know is that if that's the case, then A has an eigenvalue, lambda 1, whatever, that is real and positive. And so this is the part that we want to, kind of focus on, that lambda 1 is larger in magnitude than all the other eigenvalues. Then the long-term population will grow or shrink by a factor of lambda 1. So that's, we'll talk about, being the dominant eigenvalue, or the eigenvector that goes with the dominant eigenvalue. Okay. So, if you talk about the dominant one, like let's say you have, lambda is 2 and lambda is 5, then this would be the dominant, right? It's in absolute value. So if you had -2 and -5, then the absolute value of -5 is 5, which is greater than the absolute value of -2, which would be 2. Okay? So we can call that largest one the dominant eigenvalue. Okay. This was I was talking about earlier. If we had something with fractions here, or xt had both eigenvalues were fractions between 0 and 1, or -1, they're not bigger than 1, in other words. They're not like 1.5 or something like that, because of course we multiply 1.5 by 1.5 by 1.5 infinitely many times, that is infinity. But this is like, 1/5 and -2/5. So, as we keep multiplying them, then it's going to go to 0. Okay. So bottom of 271. Peron Frobenius? I'm not sure. I've never actually, I don't actually, it used to be called the Peron theorem, and then they added this to it. So yeah, I still call it the Peron theorem. Yeah, that's funny. Okay, so when you're looking at a recursive model, don't forget, you're looking at, some kind of recursion. So whether it be t plus 1 and t, or t and t minus 1, doesn't really matter, right? And we already know the formula, because we talked about it in the start of this section, for x naught will be given, or x of 0. So again, same as before, find the eigenvalues and eigenvectors, find the constants, and then use your formula. When it's recursive, so with an xt plus 1, xt, or t and t minus 1, there's not going to be any e in here, right? This is a recursive model, and it's not a system of differential equations. Okay, so therefore, there's no e's in this, okay? When we get to the last section, where it's a system of differential equations, then that's when you're going to see the e. Okay. So just, keep that in mind so that you can tell them apart. Okay, so consider the system of recursion. So we've got x1 of t plus 1, x2 of t plus 1 on the bottom is this A matrix, times x1 of t, x2 of t as a vector. So here, it tells us the initial condition. So x1 of 0 is 3, x2 of 0 is -5. Find the solution for x of t. So we're not going to go through any more eigenvalues and eigenvectors because we've done a ton. So whatever you want, shortcut, long version, doesn't matter to me. As long as you can get your eigenvalues and eigenvectors some way, shape, or form, then we're good to go here. Okay. So what's our xt? Well, we have xt is, you can use alpha and beta. I'm just going to use C1 and C2. So C1 And it doesn't matter the order of these things either. So if you want to put the lambdas first or the v's first, it doesn't matter. Whatever makes you happy, okay? So our lambda is -5 to the t, and that was for lambda is -5, the vector is 1, 3. Another constant, c2 or beta if you want, that lambda was 2, so 2 to the t, and that lambda gave an eigenvector of 3, 2. So that's our solution, and we have an initial condition, 3 and -5. So we're going to substitute. That's like our x naught vector, right? 3, 5. So it's going to go on the left. And when we do that, don't forget your t's are 0. So we've got 3, 5 equals c1 times -5 to the 0 times eigenvector 1, 3 plus c2 and then 2 to the 0 times eigenvector 3, 2. Now, keep in mind, anything to the 0 is gone because it's just 1. And remember, we can get an equation from the top and from the bottom. So from the top, we have 3 equals c1 times 1, so c1 plus c2 times 3. So that's 3c2. So that's the top. And then if we look at the bottom, well, you go ahead, write down what would your equation be here from the bottom. So it would be number 2, 5 equals c1 times 3, so 3c1 plus c2 times 2. And your job is to solve for c1 and c2. So, do you want to eliminate, substitute? It's up to you, right? I've got a 1 and a 3 and a 3 and a 2. So if I wanted to work with getting rid of c2, I'd have to multiply by 2 and 3 to make 6s. Here I could just multiply by 3, or my preference is always to make them opposite signs. So if I make a 3 and a -3, then I can add the opposite. If they're both positive or both negative, you have to subtract. So 3 times -3 is -9, -3c1, and then minus 3 times -3, so -9c2. And so second one just stays. So again, because they're opposites, we can add. So -9 plus 5 is so here, just writing down, I just want to check. Oh, it's -5. I knew I was missing a negative somewhere. I was trying to figure out where. Right here, guys. 3 -5. So make sure that's a negative. Otherwise, I'm going to get a different answer than what I need here. Okay. And then it'll be a crazy fraction. So -9 plus -5 is -14. And then add here, -9 plus 2 is -7. So divide both sides by -7. And my C2 is +2. Okay, so go ahead. What would your C1 be here then? What's the value for C1? I might have leave it. Yeah, I left you some room here if you want to do it here. So you could sub this back into either. I personally would probably do the first one because C1 doesn't have a number in front of it. So I'd probably say substitute C is 2 into, what was my first equation? 3 equals C1 plus 3C2. So that would be 3 is C1 plus 3 times 2. So C1 is 3 minus 6, so -3. And we already knew that our C2 is 2. And so we can just put those constants back in front of our eigenvectors and, put our eigenvalues in. And, this is our formula. And all I did here was put the C1 and the C2 in front, right, from the last page. If they want them separate for x1 of t and x2 of t, then x1 of t would be the top of everything. So -3 times 1 times -5 to the t, plus 2 times 3 times 2 to the t, and then x2 would be the bottom. Okay? And of course, -3 times 1 is just -3, and 2 times 3 would just be 6 there. If we want x of 20 or any number really, you can just sub in that number for the t. So you're subbing t is 20 into your equation up here. Now, because you're not going to be able to do that clearly without a calculator, you just have to leave these as powers to the 20, right? -5 to the 20 and 2 to the 20. Guys, that's kind of the best you can do without a calculator. And the long-term geometric rate of increase. So this was on last year's exam. They didn't word it like this year. So, whether that means they won't ask it at all, it's hard to say. I noticed that they did post, some practice exams for you, but they didn't omit certain questions, which was a bit strange. So it's hard to know. So I'm going to go through it just in case. So the long-term geometric rate of increase is going to be according to that largest eigenvalue in absolute value. So our eigenvalues were -5 and 2. So -5 absolute value is 5 is the larger one. So if they ask you about geometric rate of increase, it would be 5. And since 5 is greater than 1, it's going to be an increasing population. So it's not a fraction like a half. If they ask you in the long run, how many juveniles would you count for every adult? Well, your dominant eigenvalue is 5. And if you look back to your eigenvector, the eigenvector that was beside the eigenvalue of -5 was 1, 3. So if it's 1, 3, that means we would have 1 juvenile for every adult. Or, if it was hatchlings and adults, it would work the same way. Okay. And then they talked about long-term behavior, not as just letting x approach infinity, but they talked about long-term behavior this year in terms of a ratio. So they said to you, if x of t plus 1 is ax of t, describe the limit as t approaches infinity of a to the t u of 0. So in this case, since the dominant eigenvector that corresponds to the dominant eigenvalue is 1, 3, v1, v2, then the long-term behavior as a ratio, they would say is v1 over v2, so 1/3. Okay. So that I would memorize just in case. So that was in your notes this year, kind of a new concept, okay? So the long-term behavior as a ratio would be your v1 over v2, okay, for your dominant eigenvector, the largest eigenvalue, okay? Okay, so last section, and we're excited. So page 277. Okay, so in this section, I know there's lots to do in these questions, but like you've already learned how to do eigenvalues, eigenvectors, and all of that. So this is on systems of differential equations. So it's not recursion anymore. So they used to talk about, predator-prey questions, but they didn't talk about that this term. But that's, one of the many phenomena that we can do differential equation systems. So if we write them in a form, u1 prime of t, u2 prime of t, we can have, different functions. If it's a linear system, which is only what we're going to solve, Then we have u1 prime of t is a u1 of t plus b u2 of t plus some extra term, which could be like the number 3. Same thing for u2 prime of t. C times u1 of t plus d times u2 of t plus some other number. Alpha 1 and alpha 2 here are just constants. And a, b, c, d, again, these are just parameters. So if these alpha 1 and alpha 2s are just zeros, then that's a homogeneous system. Otherwise, it's inhomogeneous. So if you look at the notes for this chapter from Dr. Wild, I think it's chapter 8, 8.2 maybe. Anyway, the last section, you know, some of the homework's on inhomogeneous, which they didn't cover, right? So you don't have to know how to solve that. So here, if you're asked for matrix form, we've got a derivative, right? It's not recursive, so it's not a t plus 1t or a t minus 1. It's a derivative. So u prime of t so this is a derivative. We've got a u of t plus this alpha. Okay? So here, you know, we're going to have a solution because this is a derivative. The solution has e's in it. Okay? Versus recursion, which we just finished, which is totally different, where you see t plus 1 in t or t minus 1. There's no e in your solution. Okay? Okay. So write the following in matrix form. So the matrix form here would just be, we would look at this and look for our A matrix, which would just be, you know, the U1 and U2s. So this one, I kind of tried to mess with you. I wrote it in the wrong order. So if we rewrite the order, U1, U2, and then constant, then the alpha vector, the numbers that are added on is really just 0, 3. And A, the numbers in front of U1 and U2 are negative 5, 1, 1, negative 2, right? These are 1s. So that's our A matrix. So we can express the derivative u prime of t as a times u of t plus this 0, 3. Okay? Now for you guys, you're only going to study 2 types, right? We're going to have case 1 where you have real and distinct, so different eigenvalues to solve, like maybe lambda is 2 and 3, or you're going to solve the case of complex eigenvalues, right? So you're not going to cover all of the other cases. So in terms of the picture, well, if you look at the 2022 exam, that was the newest one that they posted, then, you know, in a couple minutes, we're going to do those long answers, so you'll see kind of how they asked it. So they don't ask you to draw the whole sketch or anything like that, okay? So write here as a matrix equation. So this one, they've given you, you see the derivatives here. And then you see, you know, you've got this constant here being added on. And these are the initial conditions. So if we do dx by dt is a x of t plus b. Our A matrix is the numbers in front of x1, 2, 3. So we don't have an x1, so 0. We have negative 0.2 x2, 3 x3. And this one we have 5 x1, 2 x2's out of order, negative 4 x3. And then this one has negative 4 x1, 6 x2, and no x3s. So that's my A. And my B is the numbers that don't have x's attached. So 0.4 and nothing. So 0 and 0.8. Okay. So it would look like dx by dt, or you can just say x prime would be this matrix A, can fill it in there, times x of t plus this B matrix. And you can say, you know, with x of 0 being this, 4, 3, negative 2. Okay? So if they want you to write it in a matrix equation or matrix form, that's what it would look like. And then for number 3 here, verify that this x is a solution to this. So what I would do is just a left side, right side. If I look at the left side, which is dx by dt, that's the derivative with respect to time of this x. So in other words, the derivative with respect to time of this matrix here. So think about your derivatives. Derivative e to the anything is e to the anything times the derivative of the anything, right? So here, you know, the derivative of e to the 4t would be e to the 4t times 4. So the times 4 times negative 2 is negative 8. And then e to the t derivative would just be e to the t. So that one would be okay. And then down here, e to the 4t times 4 times 2. So that'd be 8 e to the 4t plus 6 e to the t. Now we have to show that it's equal to the right side. So if we take this matrix, 3, negative 1, negative 2, 2, times x of t, well, x of t is right here. And again, you're looking at, you know, this row dot this, you know, column. So just multiplying like we did before, right? So it'd be 3 times this top. So let's see, 3 times negative 2, so that's negative 6 e to the 4t. And then 3 times this would be plus 9 e to the t. And then minus 1 times the bottom, which would just be minus 2 e to the 4t minus 6 e to the t. And then same thing, bottom row, negative 2 times the top. So negative 2 times this would be 4 e to the 4t. Negative 2 times this would be minus 6 e to the t. And then 2 times all of this. So 4 e to the 4t, 2 times that is 12 e to the t. And if you collect all those terms, like if you have negative 6 and negative 2, that's negative 8 e to the 4t. 9 minus 6 is plus 3 e to the t. On the bottom, 4 and 4 is 8 e to the 4t. And 12 minus 6 is plus 6. So you can see that it's the same. Okay, so those were a couple of questions that they kind of talked about in the notes before you actually solve the systems. Any questions with them? Okay, so if the case is that the eigenvalues are different, then, you know, if they're one positive, one negative, then it's called a saddle. It looks like this. But chances are you're just going to have to take, you know, one initial condition and just draw a sketch of just like an arrow. You're not going to have to draw the whole thing. If they're both negative versus both positives, then we get nodes, what we call them. Okay. So in our solution, take a look at how your solution differs from the one that we had before, right? In this solution, take a look. See the e's, right? Whereas when we did recursion, there was no e's, right? So now it's, e to the lambda 1t, e to the lambda 2t. So that's the difference here. Okay, and if your eigenvalue is positive, then your arrows along your eigenvector are going to point away from 0, 0, the origin. If your eigenvalue is negative, the arrows point towards the origin. And then here is talking about the sketch in each case, okay? So for number 4, we have this A matrix. We have this is a derivative. So therefore, you do need the E in your solution. It's not recursion. And the initial condition is U of 0 is 1, 8. So we do all this work to get the eigenvalues and eigenvectors, which, like I said, we've done a ton of them. So we don't have time to go through that every time, right? We're kind of done with that. So there's our eigenvalues and eigenvectors. So my solution, we know, looks like this. So this, of course, you want to memorize. So my solution is going to look like C1 e to the lambda 1 is 4t times the eigenvector that goes with lambda 1 plus C2, or you can use alpha beta again, e to the 1t. I'm going to put the 1 in just to emphasize that's the eigenvalue times eigenvector 1, 2. Guess what? Find C1 and C2, right? Initial condition, sub in your initial condition. When we sub in our initial condition, don't forget that t is 0. So we're going to put, the 1, 8 over there and let all the t's be 0. So 1, 8 is C1 e to the 4 times 0 is 0 times negative 1, 1 vector plus C2 e to the 1 times 0 times other eigenvector. Anything to the 0 is what? And I did leave you a little bit of room up there if you need it. Okay, so C1 and C2. Well, what are your equations here? What do you get for the equations, first of all? So from our top, we get 1 equals negative C1 plus C2. Bottom, we have 8 equals C1 plus 2C2. We can already add them, right? They're already the same number, just opposite signs. So 1 plus 8 is 9 equals 1 plus 2, 3C2. So C2 is 9 divided by 3 is 3. And then we can sub that back into either to find our C1. Okay, so if C2 is 3, I'm just going to put it on the top of the next page. So C2 is 3, and our equation was 1 equals negative C1 plus C2. Okay, so if C2 is 3, we've got 1 is negative C1 plus 3. So 1 minus 3 is negative 2. So C1 is 2. So my solution for U of t is 2 e to the 4t times the eigenvector 1, negative 1, and plus C2 is 3 e to the 1t times the eigenvector of 1, 2. Okay. So because we have, eigenvectors here, eigenvalues are 1 and 4. So first of all, since both eigenvalues are positive, the arrows are going to point away from the origin along both vectors. So let's plot the vectors. 1, negative 1. So go over to 1, down to negative 1. Did I write that wrong? Or negative 1, 1. 1, negative 1. I think I drew 1, 1 accidentally. No, I'll have to fix it. Anyway, 1, 2. Over to 1 and up to 2. I think this is the wrong picture that I put in here accidentally. Yes, I think I put it on the wrong page. I accidentally put the wrong picture, which means this picture is somewhere else. Okay. Well, that's not going to work too well for me, is it? Let me put it in here for you. So if we've got 1, negative 1, we would have to plot it. So if we've got 1, negative 1, I must have copied a bunch of diagrams in and put one in the wrong spot. So 1, negative 1 or negative 1, 1, same thing, would look like kind of like that. And then the other vector is 1, 2. So 1, 2 would look like that. I'll insert the right picture for you into your book tomorrow. So since they're both positive, we know that the arrows have to point away from the origin. So we've got to go away and away. Okay. And then the dominant eigenvalue is the larger and absolute value, which is 4. So basically, since lambda 1 is 4 is a dominant eigenvalue, the solutions are going to look like that eigenvector as t approaches infinity. It seems I put it into the solutions in the right order. I don't know how I did that. So it looks like this. So there's your eigenvectors, and it's going to look like the one that's dominant eventually. So we know we're going away from the origin. So if we start at the origin here, we have to go away, and we have to go away in the direction of 1, negative 1, because that's the eigenvector that goes with 4. So it kind of goes like that and like that. And chances are they won't make you draw even this whole thing. I'll show you in that, example at the end that they're just basically going to probably make you, plot one single part of it. Okay? But that's what it looks like. Okay, so number 5. So suppose, again, we have a matrix, and here's the eigenvalues, and here's the eigenvectors. Initial condition. In this case, one's positive, one's negative. So this is going to be what's called a saddle. You don't need to know the terminology, but it's a lot easier to draw out. So basically, if we plot these two vectors, if it's positive, the arrows are going to go away from the origin, and negative, the arrows are going to point towards the origin. So if we draw the vector 1, 1, so over 1, up 1, so it's going to go 1, 1, 2, 2. Draw some of those in just to get a better line. And that is the vector 1, 1, which goes with lambda negative 2. And then our other vector is 1, negative 3, which is the same as negative 1, 3. Remember, eigenvectors always go through 0, 0. So that was lambda is 4, and our vector is 1, negative 3. So let's see. Negative, if it's a negative eigenvalue, arrows are going towards the origin from both sides, pointing towards. And if it's a positive, then the arrows are going away from the origin. Negative is toward, and positive is away. And then again, they'll probably just give you some kind of initial condition. So if the initial condition is 3, 1 here, so this is what they did on the 2022 exam, I think it was. So plot this condition, 3, 1, and then saddles are, in my opinion, the easiest to draw. It's going to follow this kind of going in towards the origin and then going out this way. So it's just going to go in towards and then out. And that's kind of all they're going to be looking for. Okay. If I gave you maybe a different condition, so this was u of 0 was the vector, the 0.31 here. So if we do, let's say, -3, -1, then it's going to go in towards, and then it's going to go that way. Okay, so that's basically it. And for complex, it's just going to be like a spiral for complex eigenvalues. Okay, questions? Okay. So complex, the solutions look very annoying. We know from before we have A plus or minus BI, complex conjugates. So if we look at the eigenvectors, we have a real part X, an imaginary part Y. And the solution looks like this. And A and B are from your eigenvalue. So it is like really, really intense looking in terms of the solution. Okay. So C1 e to the AT, bracket cos BTX minus sine BTY, plus, and then the C2. E to the AT, sine BT times X, plus cos BTY. And so if it's going to be complex, then we can say, basically, the vector is going to point, if we look at this, A matrix, if we have this A to 1, the bottom left, if it's positive, it's going to go counterclockwise. If we have the A to 1 is negative, it's going to go clockwise rotation. Okay. So you can read through that, but I'll show it to you here. So on 287, if we solve this one, well, again, eigenvalues, eigenvectors. So here's the eigenvectors. And if we look at this, here's our vector. V1 is 1 plus 2i and 5. So if we write this as something and then plus something times I, this is the x part, the real part, and there's the y, right? Y is the vector beside the I. And since our lambda is 8 plus 2i, that's A and that's B in our solution. Okay. So our answer is just going to be the A and B get put in here and here, all the A's and B's. A is 8, B is 2 from this, and then my X and Y, right? X was 1, 5, and Y was 2, 0. Okay. If they make you sub an initial condition in, then obviously you're subbing in the initial condition over here like before, and all your T's are 0 like before. Okay. So what's it look like? Well, if it's complex, if there is no real part, it's just a closed ellipse. So that would be plus or minus 8i, something like that. If you get A is positive, so 8 plus or minus 2i, then the a part is positive, then it's going to spiral away from the origin. If your a is negative, then it's going to spiral towards the origin. So like this, let's say we have, something like this, then that's a negative. So that will spiral towards the origin. So for my example, I gave you 8 plus 2i, so that's going to spiral away. Okay. And this was my matrix. So I can look at the 2, 1 spot or the 1, 2 spot. The 2, 1 is 5, so it's greater than 0. So it's going to be moving counterclockwise. And the 1, 2 spot is negative 1, so it's going to be moving left. So it just kind of, if you plot the initial condition, which is 5, 5, it's just kind of moving left and around, and it has to go away from the origin because our a is positive. And again, they'll just be looking for like a super, super quick sketch, right? Nothing, major there. Okay, this is the summary of how to tell those two questions apart. So here are the two exam questions. So number 7 and number 8. So 7, see how 7 says, consider an age-structured population made of juveniles and adults. Each adult in year 1 produces an average of 27/4 juveniles counted in the next year. Okay, so adult to juveniles, 27/4. Each juvenile we count in 1 year survives to be an adult in the next year with probability 25%. Okay. So 25%, so let's just say 1/4. Okay, so that's juvenile to adult. Okay. And then each adult in 1 year survives to be counted as an adult again in the next year with probability. We're going to have to change this to 3/2 because the numbers were just even worse than horrible. So change that to 3/2. And that's our picture here. Now, the numbers that they gave on the exam when they gave 2 questions like this were horrible too. They were horrible, like with fractions. And, I think I told you that, they said like they just had so much trouble with the numbers. Okay. Maybe you guys will get lucky and there'll be no fractions, right? So if xt is the number of juveniles in year t, yt adults, and x naught is 24 and y naught is 8, find an explicit expression. So this is juveniles and adults. It's recursion. There's not going to be an e. So my xt, yt, or you can say just juvenile adults, doesn't matter as long as you know how to write your matrix. So juvenile to juvenile, there's nothing. Juvenile to adults, juvenile to adults is 1/4, so that's x to y. Adult to adult is 3/2, and y to x is 27/4. And again, you can do t minus 1s, or you can do t plus 1s and t's. It doesn't matter, right? So my A matrix is 0, 27/4, 1/4, and 3/2. Okay, well, you know what we're going to do, right? We're going to find our eigenvalues, find our eigenvectors, and then get our solution. So it's going to be all the same as normal, like that a minus lambda I equals 0. So we take our a, minus lambda times I equals 0. So we'd have det 0 minus lambda, so negative lambda, 27/4, 1/4, and 3/2 minus lambda. we do our AD minus BC. And so we got negative lambda times this would be negative 3 over 2 lambda. Negative lambda times that would be plus lambda squared minus 27 over 4 times 1 over 4 is 27 over 16. So if we write it out like this, we have to factor this, right? So can you factor that easily just by looking at the fractions? Maybe. If you can, great. If you can't, because it's kind of insane, you could also multiply it by 16, and then that will get rid of the fractions, and then hopefully you can factor it like that. Either way, it's not nice. So we know that 4 times 4 is 16, and then we can make it work to get 27, which would be 9 and 3. So you could try 3 and 9 or 9 and 3 until you get it to multiply out properly. This is what works, because that's 16 lambda squared plus 12 and minus 36. Positive 12 and minus 36 is negative 24, and then negative 9 times positive 3. So if 4 lambda minus 9 is 0, then lambda is 9 over 4. And here, 4 lambda is negative 3, then lambda is negative 3/4. Okay. And then, of course, we can put both of those in and find the eigenvector. Okay. So you can see how it's a lot of work. And the fractions don't help, right? So once we find the eigenvectors, the V1 ends up being 3, 1, and the V2 is 9, negative 1. And of course, you're going to do, through a whole A minus lambda I, V equals 0 to get your eigenvectors. Just like we did, 5 or 6 times today. Now, once you've got that, it's recursive, right? So we know our formula is C1 V1 lambda 1 to the t plus C2 V2 lambda 2 to the t. And then, of course, just like always, we'd have to find our C's. So our first vector, 3, 1, eigenvalue 9/4 to the t plus C2, second vector times negative 3/4 to the t. And remember, the order of these three and these three doesn't matter. Okay. So, a lot of work. Questions? So what would be the long-term geometric rate of increase, and is it growing or shrinking? So that was the part B they asked. So we need to figure out which of these eigenvalues is dominant. Well, the larger in absolute value is this one. So 9 over 4 is the dominant eigenvalue, the larger in absolute value. So we can say the geometric rate of increase is 9 over 4. Is it growing or is it shrinking? Well, it's above 1, so therefore it's a growing population. And the last part is, in the long run, how many juveniles should you count for every adult? Okay, what do you think? We talked about this earlier. What do you think it should be here? Well, it's according to the eigenvector that goes with 9/4, which was 3, 1. So juveniles would be on top, adults would be on the bottom. So in the long run, we expect to count 3 juveniles for every 1 adult. Okay, so that's a recursive example off an exam, different numbers, but the same craziness in the numbers that they gave, okay? So the last one now is, what happens when they give 1? That's a system of differential equations. So then, of course, we have that E, okay? So we can tell this is a system because, look, we've got U1 prime, U2 prime. We know we've got derivatives. If they give you an initial condition, then yeah. If they give you an initial condition, then you would solve for x naught. So I just don't have time to go through all this, right? Because the session's basically over. But yeah, same thing we did in all the other examples, right? I think we've done like 5 of them now. So yeah, put your x naught, y naught in and find your, 7t is 0. Okay, so if you see derivatives, then we're looking at u prime of t is a u of t. So our A matrix is the coefficients in front here, 4, -1, 2, 1. And it's a system of differential equations. So it's got to have an E, right, in our solutions. So again, same thing as always, right? Go through, find det A minus lambda I, solve. We're going to get 2 eigenvalues that are distinct. Then, for each of them, A minus lambda IV equals 0. Find your eigenvectors. So my V is 1, 1 and 1, 2. So this one is for 3 and this one is for 2. Okay, so again, you can try later finding your eigenvalues and eigenvectors. So once you get that, what's your solution going to look like? Well, you're going to have your u of t, c1 v1 e to the lambda 1t, plus c2 v2 e to the lambda 2t. So if these are your 2 eigenvectors, and these are the corresponding eigenvalues, and these are your 2 corresponding eigenvectors, fill it in. What would your solution look like here? Well, we'd have C1 times vector 1, 1, e to the 3t, and then plus C2, V2, e to the 2t. And again, we do have an initial condition 0, 3, so yes, we'd have to sub it in, right? Along with t is 0, right? So we could put in the condition 0, 3, and then, do the whole 0 for all the t's. And then you could solve for C1, which should give you -3, and C2 is 3. So this is what we had here and here, and then these are our constants. Well, what would your final answer to your solution be then, if you were to put these in? We would sub them back in there, basically, right? So we would have u of t, C1 would be -3 times 1, 1, e to the 3t, and then C2 is 3, so 3 times vector 1, 2, and then e to the 2t. Okay. And then they had them sketch a solution, a couple solutions, okay? So, well, in terms of our eigenvalues, let's do that first. So if lambda 1 is 3 and v1 was 1, 1, that one's a positive. And if lambda 2 was 2, that was also positive. And v2 was 1, 2. So, quick sketch, let's see here. So if we plot 1, 1, so 1, 1, negative 1, 1. And then our other vector is over 1 up 2. So always through 0, 0. So negative 1, negative 2 as well would work here. And that's the vector 1, 2. And think about your arrows. They're both positive. So the arrows point away from the origin. So away and away. Same thing here. And what's our initial condition? It says the initial condition from part A, which was what, guys? 0, 3. So 0, 3 is kind of here. And you're not going to actually cross this eigenvector, so it's just going to kind of go like this. Okay, so that was the solution they were looking for. And then in part C, they asked for a different initial condition. Okay. Now, if they ask you for a condition that is going along an actual eigenvector, which in part C, they asked for negative 1, negative 2. Well, negative 1, negative 2 is right on that vector. And so it's just going to go like that. So that would be the answer to C. Now, they had to draw it separately, so they just probably would just draw that one eigenvector. But yeah, so this would follow along. This line would just be, U2 is 2U1, right? Because it's 1, 2. So just like y equals 2x equation, right? Okay, and it would go away from the origin because of the positive for the eigenvalue. Okay, so that's what we're looking at in terms of the very end of the course. Okay, so you have lots of practice to do, obviously. Practice lots of eigenvalues, eigenvectors. I'll fix that graph and put that in for you tomorrow. I'll also put in the solutions, how to get from one of those solutions with I to the other one, in case you're curious. Yeah, and so otherwise, just do lots and lots of practice, do all those exams I gave you, and I hope everything goes well for you. So good luck on all of your finals. I know it's a hard time, so do the best you can, study hard, you can do it, and have a great, relaxing summer when you get there, okay, guys? So hang on now if you have questions, and otherwise, hopefully I'll see you next year for a course, okay? Take care, everybody.